Okay. This talk is about the Bitcoin Relay Network. I swear it's not a talk about the block size. I will try to avoid mentioning the block size repeatedly, but I probably will fail. Yeah, so I'm Matt. I have been running the Bitcoin Relay Network for several years now, and it's unrelated to any employer or anything else. I do work for I'm a co-founder of Blockstream, but this has existed since long before then. So anyway, yeah. So the Bitcoin Relay Network grew out of two main concerns that were kind of rather popular, I guess, a few years ago, 2 years ago. The first was that at the time we were just seeing a rapid drop-off in the number of listening nodes on the network, listening full nodes on the network. So we had just seen a rapid spike in January 2.5 years ago, I think. And then not long after that, it just kind of kept going down and down and down. We only had a few hundred listening nodes on the network. So this was really a concern for two reasons. The first is that it indicates that people are kind of reducing their trust model, right? So there's a bunch of people who no longer care about being full nodes. They just want to run an SPV wallet, or they just don't want to listen. But the big concern that the Relay Network wanted to address is that it means that this valuable resource of the number of connections that are available on the network to new people who want to connect to this peer-to-peer network has decreased hugely. So there's only, maximum 125 connections that each node will accept if it's listening. And those are pretty easy to eat up pretty quick. Not to mention if there's only a few hundred nodes, to DDoS a few hundred servers offline is pretty cheap, especially since most of them are just running on a VPS provider somewhere. So this was a big concern that this peer-to-peer network is potentially somewhat fragile just because it's not, there's not that many nodes listening, and you could take them offline pretty quick. So the Relay Network really wanted to address part of this by running kind of a backup secondary network, right? So it's this pseudo-centralized network that will relay blocks between nodes or between nodes who are connected to it. It's kind of a centralized hub and spoke network. But I'll get into that in a second. So it's kind of complementary to the peer-to-peer network. The second concern that was really a forefront in the community, especially with regards to mining, was the selfish mining attack. So this paper had come out 6 months or more before I started the Relay Network, and no one really had a great response to it. For those of you who aren't familiar, the selfish mining attack, essentially, the paper claimed that you could, with 33% of the network, gain an advantage similar to a 51% attack, at least in the short term, as a miner. So the way you do this, you just you don't announce your blocks as quickly. You keep your blocks hidden from the network, and then when someone else announces a block, you try to propagate your block quicker than theirs. If you have less than 33%, it's potentially doable if you can propagate your block faster than anyone else because you have better visibility into the network. So this peer-to-peer network is kind of random, and we don't really have good measurements of who peers with who and who's connected with who. But if you're a miner and you can potentially make a lot of money, you're hugely incentivized to go figure out how the network looks today, where all the miners are in the network, try to peer with all of them, and get better visibility into how the peer-to-peer network is laid out effectively than all the other miners, which means you could potentially do a selfish mining attack with less than 33% of the network. So this was also a big concern. And the Relay Network's goal really with this so we're going to set up this alternative second network that's a backup to the peer-to-peer network, and also create something that will try to peer with all of the miners and try to put in the work to make sure that it gets blocks very quickly and gives blocks out to everyone else who's connected to it very quickly to try to make it so that selfish mining doesn't work because you can't gain an advantage on the network because everyone's just going through the Relay Network at least. The Relay Network is very quick and will stop you from getting an advantage. So generally, the Relay Network started as, let's just get up some nodes and try to peer with everyone. So it started as a bunch of SPV nodes around the globe. I guess I don't have a map here. I do have a map. Okay, so it started with a bunch of SPV nodes around the globe. It was actually just New York, Seattle, Amsterdam, and Singapore at the time that were just listening and were relaying blocks before validating them. So the idea was basically all the miners would connect, and they would, as a part of being connected to a node, announce their blocks, and then they would get relayed around the globe without stopping to validate at each point, which is really a part of what slows down the Bitcoin peer-to-peer network, and then we can get them around the globe much quicker. So that ran for a while, and there was some potentially anecdotal evidence that maybe it did reduce orphan rates when it first launched. It's kind of unclear, it's kind of hard to measure, but orphan rates did drop around when it first launched, so maybe they were related, it's hard to tell. So that ran for a while, and then I started doing much smarter things than just running simple announcing blocks around the globe. So there's this wonderful chart that is from the stats page of the Relay Network today. You can see on this axis, you can see the size of the block as it was compressed. So the Relay Network takes blocks and tries to compress them down on the wire. And on this axis, you can see how long it took for the block to get all the way around the Relay Network. And they're both log scale. And you can see that there's a very strong correlation here, right? So if we're going around the globe on TCP, it turns out TCP sucks. And TCP, even if you're connected to all of these servers are connected to gigabit lines, the thing that matters is not how fast your line is. If you're crossing the globe, if you're crossing an ocean, what matters is your latency and your packet loss. So even if you're only broadcasting, let's say, 1,000 bytes, getting around the globe, you start to notice a very 10,000 bytes or so. Getting around the globe, you start to notice a very drastic increase versus when you're transmitting just one packet. So, in response to this, right, the Relay Network compresses blocks. It has a little, uses the thought that Bitcoin already has announced most of the transactions that are in each block, and everyone has already seen most of these transactions, to just point to an indicator of the transaction, right? So, on the wire, all we send is we send 4-byte magic, 4-byte thing that says, hey, this is a block, 4-byte thing that says the number of transactions in the block, 80 bytes for the block header, and then we say, for each transaction, we're either going to say the nth last transaction, which is just 2 bytes. We say, hey, the transaction I sent you 5 transactions ago, or we drop out and we say, the TX size, and we send the whole transaction itself, 5 extra bytes. So this beats the standard Bitcoin encoding of a block rather significantly. So this graph right here is in the last 48 hours or so, and I took this a few hours ago. You can see the top line here is the size of the block itself. So most of them are right around a megabyte. And again, this is a log scale graph as well. And then you see this red area graph right here is the amount of actual data that cross the Relay Network. And you can see that most of them are written about 1 kilobyte to maybe about 5 kilobytes. Actually, you can't read it, but right at the title of the graph it says that 38% of blocks were sent around the Relay Network in one TCP packet. So if you know anything about packet networks, you know the difference between sending 1 byte and 1,480 something bytes is pretty much negligible because it's one packet either way. It's one packet on the wire. So the Relay Network does very well. It gets 38% of blocks in one packet and 67 or 68 in 2 packets, which means we have way lower rate of loss. And if we lose 1 packet, we have the same rate of loss rate. So most blocks are in 1,000 packets. And if we lose 1% of packets, we're likely to lose a packet, which means we have to wait an entire round trip to figure out that we lost a packet and send the packet again. Versus if we're only sending 2 packets, then we don't have to wait all that time, which means everything's much quicker. So yeah. Magic compression, yeah. Yeah, so the other important thing is the Relay Network is in well-peered areas. You'll notice Asia looks kind of complicated. There was just 2 nodes in the US, 1 in Europe, no big deal, right? But there's lots of peering going on here in Asia, and I even have a node in the middle of nowhere in Siberia. So it turns out peering in Asia sucks. It is an absolute mess. If you route a packet from Beijing to Singapore, almost always it goes through LA. If you route a packet anywhere from China to anywhere else in the world, almost always it goes through LA. Because most of the cables coming out of China stop in Tokyo and then go straight to LA. So, of course, I have a node in Tokyo because routing between Tokyo and China is pretty good. And the only exception to this is if you're going to Europe through Russia. So there's one cable that crosses land in Russia here. It's actually pretty optimal. These lines are the optimal distance, the way a plane flies. I guess geodesic. But the only way to use that cable is if you stop in Russia, because the only people who actually run through that cable is if it's going through Russian telecom, which peers with Chinese providers and European providers, but they don't allow people to necessarily transit across their routes. So you have to stop in Russia to get decent peering between China and Europe. And in fact, this one node reduces latency between several miners in Europe and several miners in China by a few hundred milliseconds. Just latency, and remember, if we lose a packet or two, that could blow up to 10x that or more as a ratio of latency. Yeah, so that's also why there's a node in Japan, right? Because everything stops going out of Japan. And then also, the only quick way to get from Asia to Europe in general is if you have a node in Singapore, because everything else routes through the US, because, I don't know, there's more cables to the US or something. Except for Singapore, which also happens to be good. So there's a lot of work that was gone into just picking where these nodes are and how they peer with each other. Now, if you're a small miner, and you have a small mining operation in, let's say, Australia, I don't know why, I think power is expensive there, but whatever, you decided you wanted to mine in Australia. If you want to be competitive with the large miners, say the large Chinese miners, who all spend a reasonable amount of time and money to buy nodes around the globe and to optimize the block propagation of their blocks between their nodes around the globe, you're going to have to put in as much effort as I did to figure out why routing sucks everywhere in Asia and figure out how to work around that by picking locations of where to put your nodes. So that's a rather steep cost that each small miner would have to put in if they wanted to compete with the large miners. So this leads into the next point about centralization, right? So there's a lot of people who complain when they see the relay network that this is centralizing Bitcoin. And it is, because if you want to get your blocks around the globe quickly, you now have to use this network that is run by me, exclusively by me, and you have to go through me. That sucks. So when you think about something like this, you have to think about what is the opportunity cost of not using this network, and what is the opportunity cost, or what's the necessarily, how efficient can we make this decentralized network versus how efficient can we make a centralized network? So it's important to note, before the relay network, and even after the relay network has existed, most of the large miners, especially like the guys in China who have big peering issues and have big latency issues, they have spent a lot of time already dealing with their own block propagation networks where they have nodes around the globe and they have a better compression algorithm than mine because they already know what they're going to mine. And they've already put a lot of effort here. So if you're a small miner, you're kind of already at a disadvantage if something like this doesn't exist. So this is already an inherent centralization pressure, right? That you can get a better orphan rate than other miners if you're larger because you can put in a lot of time to figure these things out. So thus the relay network exists to hopefully reduce the centralization pressure by providing, at least, I've also kind of documented where these nodes are and why, at least in this talk somewhat, so that people can see this. But let's think I don't really want to talk about the block size, but no, okay. But yeah, so the Yeah, so if you are, yeah, so the opportunity cost of having this, this is the size of things going across the wire, and it is only at 1 megabyte, and the latency around the globe goes down rather drastically in a heavily optimized network. That's only 1 megabyte. This is only 1 megabyte. This is 1 megabyte right there. It took like 10 seconds. And yeah. This does not lead into the block size-ish. But the other point to make about centralization, about all of these, about this system and all of the other systems that people have proposed about compressing blocks. So there's been a lot of proposals, especially in the block size debate, because people know that, at least somewhat know that TCP sucks and like announcing blocks around the world is really freaking slow. So a lot of people have proposed like, okay, well we have like the relay network protocol, which does the simple compression of like the last transaction I sent you or whatever. Or there's a bunch of fancier schemes. There's IBLT, which is invertible Bloom filtered table lookup, something or other. And then there's some O1 stuff that is really fancy and potentially compresses blocks, but all of it relies on one thing, and it relies on that you have synchronized mempools and that you have a similar policy for what gets into your mempool and what you mine in a block. So the relay network, I mean the relay network definitely does this as well. These blocks that didn't compress very well up here, it's because the transactions that they included in the block weren't already in the mempool of the relay network, or the relay network didn't accept them because they were too large or whatever. And that means they had a rather drastic increase in potential orphan rate, right? If it took 10 seconds, so 10 seconds when blocks are every 600 seconds is about a 1.6% increase in orphan rate. That's huge if you're a miner. And that's only because you chose to include different transactions than what the relay network or what your other peers, if you're going to do a compression scheme across the peer-to-peer network, if you use a different set of transactions, then all of a sudden, like, your propagation sucks. And this is potentially a huge problem for Bitcoin, right? If we start relying on people having the same mempools, then all of a sudden, like, people who want to include transactions that are potentially being censored by other miners, so maybe a miner has a court order to not include a certain transaction, all of a sudden, if you are violating that court order that exists in a different country that you don't care about, now you have an increased orphan risk, and it becomes harder for you to include that transaction as well. It costs you money if you have an orphan, or you don't necessarily want to risk it. So, yeah, we got to be careful about these compression schemes, especially when we're talking about like, well, we can increase the block size because we can compress all the blocks across the wire, and then it's not a huge deal for wheeling around the globe, right? So yeah, I also want to point out, like, please help with this. This is a project that I've been doing for like 2 years. I'm currently spending $40 a month to run all the servers. They're cheap, but like, donate, because I could use some change to run these, to pay for these servers. Also, like, help with the code. It's on GitHub. There's a bunch of issues that are already filed that should be rather easy for someone to pick up and go. It's a much smaller piece of software than, say, Bitcoin Core, and you can get started with it much quicker. If you do a decent job, you can increase the effective hash power of Bitcoin just by writing some software, which increases its attack resilience, which is great. You can potentially help small miners. And also, like, it would be great if we worked on better compression protocols so that we didn't have things like the issue where potentially you have unsynced mempools and you lose out just because of that. And we can do marginally better. Like, the relay network has one synced mempool globally that ignores if miners send it transactions it doesn't like. But we can do better. We can accept transactions that we can relay transactions around that miners really want to include under some criteria of like, this is potentially being censored elsewhere. there's a lot of things we could do, but check out the issues list. Help me out. Yeah. Okay. That was it. Yeah. Thanks. Yes.
So let's pretend I don't know very much, which wouldn't be hard. What does your code do that's at relay node?
It's mostly just the compression function. I mean, it's
mainly compression.
It's mainly just this compression stuff. It's not much code. I don't actually know offhand how many lines of code it is, but there's a bunch of networking code, and then it does the compression runs, and that's about it. Yes.
I have a question. So what is the, I guess, advantage of, like, I don't know, a 1 second versus 10 second, like, transaction speed?
It's blocks, right? So if your block takes 10 seconds longer, right? So let's see, we have, yeah, so these blocks relay around the globe in 100 milliseconds, probably wrong, but a few hundred milliseconds, like between 200 and 500. I guess between 200 and 300 or so is like pretty common. If your block takes then a second plus 10 seconds plus 200 milliseconds, like apparently this one did, then that's a 1.6% decrease in orphan rate. So it's, the number of seconds divided by 600, which is the block increase. It's like roughly a large decrease in orphan rate, which directly means you lost 1.6% of profits. Your profit margin went down to minor.
And orphan rate is like the chance of your block not counting?
Yeah, sorry. So an orphan is if someone else finds a block before you, and then eventually other miners build on the other block, so your block is now worthless.
Got it. Okay, cool. Thanks.
A loss of money. Yes.
So this daemon, it connects to Bitcoin D node on 8333 and then
Yeah, it's just a proxy.
it talks.
It just like talks to both sides. It talks to the relay network, talks to your Bitcoin D, and sends it back and forth. That's where most of the code is, just like connecting back and forth to things, networking
Use a lot of
stuff.
the same code as Bitcoin D.
No, it's all custom code. Because Bitcoin D's code's a mess.
It's in C.
It's in C++, yeah. Yes.
Yeah, I just want to clarify, when you say compression, you're not really talking about compressing the data itself, but just the reduction in the amount of data being transferred across the network for specific metadata about.
Yeah, I mean, it's I guess nothing is technically compressed in the same way. The block is compressed because it already has sent the data, but the data has already been sent over the same connection. So it's not like it's using XC or something.
So they trade transactions too, not just blocks.
Yes, it relays around transactions first and then relays blocks smaller because it has already relayed a transaction. Same as Bitcoin D because you already have a mempool, right?
And that's a guarantee that it only ever forwards a block if you can also send the
It
transaction.
forwards all blocks, so it has this dropout, right? So you can either use 2 bytes per transaction or 5
So
plus
it
the
could
transaction.
forward a block that has never gone over the relay network. That includes transactions that were never in the relay network.
Yeah, I mean, that's why the compression sucks for these ones.
Okay.
They didn't have their
You
transactions in the
could
memory pool.
potentially choose to always send those transactions first before you
This
send the
doesn't
block.
save you anything. So the reason those transactions weren't sent first, right, is either because they didn't match the mempool requirements of a random Bitcoin D, but more likely it's just like they weren't seen already. So like, for example, F2 Pool has mined a bunch of blocks recently that has like 500 kilobyte transactions that were never broadcast on the peer-to-peer network. They were just first seen in the block.
And so you could say, as a policy, always send that transaction before you send that block header.
I mean, that doesn't save you any time, right? If you send that transaction first, it compresses the block more, but it doesn't save you any time at block time. Like, the thing that you really want to optimize for is you want to optimize for, I saw a block from someone, I want to get the full copy of that block around to everyone else. So
If people are really counting on the network, the relay network, for a canonical serve of what's been seen, I mean, you can fix that so that they would never ever have a transaction as long as they kept connected to the relay network that they haven't seen when you send out a header.
I'll never have a transaction I haven't seen. Like there was no way to have seen them before the block.
So people are going to have to get them from somewhere.
Yeah, they go over the relay network.
Why wouldn't they go over the, okay, but why wouldn't they go over the relay network before you send out the header?
Because no one has seen them beforehand.
That's fine, but when you get the block and decide you're about to send the block header, why not send that transaction first.
You could, but it doesn't save you anything.
Just
It's the same amount of time. It's the same amount of data on the wire.
It does if you send that block header, and maybe it takes a whole bunch of other transactions that aren't even in the block yet before you get to the one.
It
It's the same.
maybe simplifies the
You don't
protocol,
have
but
that
that's it.
breakdown of the protocol.
Yeah, maybe slightly. Maybe saves you a few bytes. Maybe? Probably not. I don't know. Yeah.
You compress the transactions with zlib or something?
No, I mean, the transactions are mostly random data, right? Transactions are mostly like... Can you repeat the question? Oh, yes. The question was, could I compress transactions with zlib? The answer is, like, transactions are mostly random data. They're mostly, like, a public key and a signature, which looks completely random on the wire.
But it's definitely not uniform.
Yeah, so you could compress it somewhat. You could do some smart things, like you know what most transactions look like. Most transactions are like you know what most transactions look like. You could do some things that are smarter. Like you can see like how Bitcoin D stores the UTXO set. They're like have some smarter things. Like this transaction looks like a standard whatever form. Thus I can save a few bytes. You're only going to save a few bytes, and mostly you're optimizing. Mostly you don't care about the transactions as they go over the wire. You care about the transactions that are in the block, and mostly those are 2 bytes each anyway, so it's not necessarily something you need to optimize as much for.
Right, so you said TCP sucks like a few times. Have you looked into possibly like optimizing the TCP stack on the nodes themselves, like using congestion windows or like switching to like a congestion board?
Yeah, so...
Can you repeat the question?
Yeah, so the question is like, I said several times that TCP sucks, and the question is like, have I looked at optimizing TCP on the nodes, like changing the TCP stack, whatever. So much of the reason TCP sucks is kind of inherent here. It's like packet loss means you need a round trip to find out that the packet was lost. The thing that I could do that's kind of obvious is I've thought about writing a little PCAP daemon that sits on the wire and listens to all packets and resends them again 10 milliseconds later, so that if you have packet loss, you've resent the packet already, it doesn't matter. That would potentially work, and I haven't studied it. That's just like a toy idea I've thought about. The other problem is like many of the nodes are like OpenVZ, so I can't fuck around with the kernel too much, which is annoying. But like, hey, if you don't need more money, I can buy fancier nodes, and then maybe I can do that. Yeah.
So is your system intolerant to loss that you could not, for example, use UDP and what would happen if you really lose a packet?
Yeah, so the question was like, is the system intolerant to loss? Could you just use UDP? The answer is, I could use UDP, but then I reinvent TCP on top of UDP. There's a lot of people who've done this, and it generally doesn't end that well. Maybe you could be a bit more efficient. Yes, UDP is a great example. Thank you, Graham. Although, to be fair, the reason UTP exists largely is because it wants a different control flow, or a different flow control, which is somewhat legitimate because kernels suck and they don't let you pick your flow control. Yeah.
Have you looked at Click?
Yeah, so I haven't spent too much time looking at like alternate TCP replacement things. Again, they kind of all are gonna suck because it's inherent. You lose a packet, you have unless you're broadcasting your packets twice. If you lose a packet, you have to wait an RTT to hear about the packet again.
You may want to look at Click because I mean, it's Google. You know, I mean, they look at TCP's problem.
Yeah. I mean, it's the only. I guess in theory, right? TCP. Unless you see so much packet loss that you see TCP back off during sending a block, which I haven't studied about the particular servers, but most of the stuff between the servers, between clients and the server is like, you know, very low latency, close links that probably don't have much loss anyway, so that's not a concern. It's really the concern across the long haul links. And across those links, like, again, I haven't looked in detail about whether like TCP is backing off a lot, but they're long-running links that are sending small amounts of data constantly, so there shouldn't be too much back off, and thus the only reason you should see like loss of performance, like you should be seeing like TCP SAC and everything, like the selective acknowledgement stuff, which should mean that the only time you should wait really more than 1 or 2 RTTs to send to resend packets is if you have loss like right towards the end. Yeah, I think a large motivation for Quick was like to fix HTTP stuff too, and not just.
You might be getting weird artifacts of your window size under those circumstances.
It's also, yeah.
For that, so occasionally the window size might collapse too much and start slowing you down.
Yeah.
But mostly your problem there is that all congestion controllers are going to be designed to send slower when there's loss, and you don't want them to send slower ever. Just keep sending faster.
Yeah, so Bram's point was that you could just be seeing decreasing window size, which yeah, it's just like doing back off, right? Which yeah, I mean, it could just be because of loss, that it's backing off a bunch and just being really slow, which would explain some of the like really long tail stuff, but most of the stuff is pretty quick anyway, which seems to indicate, like most of the stuff down in the like 500 milliseconds range seems to indicate that you're only waiting 1, maybe 2 RTTs for like 1 or 2 lost packets. So there's some long tail that could be optimized by doing some of the fancier stuff, but 500 milliseconds around the globe, it's 1, maybe 2 RTTs between most of the servers. That's pretty quick anyway.
2 RTTs between the longest points on it.
Yeah. So it doesn't seem to be too much of an issue. Yes.
So how definitely did you deploy these nodes around the world, like in Siberia? Is there some service there that's...
Yes, there are VPS service providers everywhere. The question was like, how did I put a server in Siberia and various other places? Turns out there are VPS service providers literally everywhere in the world. If you can think of a city, someone is probably selling a VPS there, and usually it's like $5 a month, maybe
Auckland.
3.
You need to cover Auckland.
No, I don't need to cover Auckland because there are no miners in Auckland.
Miners in the Southern Hemisphere.
Yeah, I don't think there's much of any mining in the Southern Hemisphere. It's a good point.
If so much traffic goes to LA, why don't you have a node in LA?
Traffic from Asia goes through LA, but traffic in general is not. So there. Let me go back to the map. The question was, if so much traffic goes through LA, why don't I have a node in LA? Oh, you can't even see the map. Anyway, so I have. Yeah, okay, so Seattle. So from the U.S. the Western Seaboard to Asia, you have 3 points that they lead from. It's either LA, SF, or Seattle, and they all there is sufficient direct routes from Seattle to Japan and Singapore that is fine. Mostly the traffic that goes through LA is from China because I think it's China Unicom, maybe it's China Telecom, one of the two. Most of their stuff, their main cable to the rest of the world, and especially the U.S., goes, I think, 3 points on the Chinese coast to Tokyo to LA. So it's mainly just stuff from China that goes through, that always goes through LA. Some other stuff does, but also I think Seattle because there are some miners in Washington, and there are not, as far as I know, many miners further south because power is cheaper up there.
This projection is very misleading here. You really want this clustering to be looking down on it from the North Pole, which will show up looking much more clusters.
Bram's point was that the selection of map projection is not optimal for viewing this data. Thank you, Bram.
Mercator. Fascinating bits about how you research the nodes. I'd love to hear a little bit more about that. But also, how many false blocks do you get on the network?
And the question was how many false blocks I get in the network? I'm not sure what you mean by that. I'm assuming you mean like invalid blocks.
Invalids.
The answer is that the network checks some basic things about the block. The network checks that your Merkle tree matches and that you have expended a lot of difficulty to make the block. So I'm not. The only false blocks I've gotten was when like F2Pool was mining the invalid blocks because F2Pool and several other miners were mining the invalid blocks not too long ago because a soft fork had happened, but some people had just changed the version number on their blocks and hadn't bothered to. Sorry, that wasn't the problem. Anyway, a soft fork had happened and some people were mining invalid blocks and some other people were like building on top of those invalid blocks, F2Pool being the primary offender there. And so like, those are the only invalid blocks I'm aware of, but like, it's a low enough percentage rate because to expend that much difficulty to build a block is kind of ridiculous if you're not going to build something that's going to get you money in return.
So you check, that's actually a pretty good assumption, just checking the difficulty.
Yeah, I mean, yeah, it's not a sufficient assumption for like actually relying on payments, but if all you're going to do is cause slightly more load on the network, whatever.
Smart.
Any further questions? Yes?
turn off your judgment for a second. Your $40 a month cost is less than a penny a block. Blocks include a penny payment to you. You only check them once. And if they don't include a penny,
Yeah.
double check just in case of bit errors in your math.
This is true. There are many examples. So, proposed a way for me to charge money directly to miners for using the service. Yes, there are many examples of ways that I can charge miners to use the service. Really don't want to do that, mostly because one of the key reasons for it existing, right, is because there's a lot of large miners that already expend a bunch of money to build good networks. So like then I would only be charging small miners because big miners wouldn't care. And then I wouldn't have good peering with large miners.
Proportional to their effort. Right?
Yeah.
It's perfectly fair.
Yeah,
There's no price.
So I can say that like the node in the only node I don't pay for is the one in Beijing, and that is sponsored by F2Pool, who provides me a free VPS, which is great. I would love for more miners to like pay for the service they're using. There are several miners who are seemingly incompetent, who I know who definitely use the service for a lot of their blocks, for like the main uses of a lot of their blocks. I think by far, like the whole China to Europe route, no one else does that very well.
They're incompetent, so their hardware might be flaky.
Yeah, but they also don't really notice that they're like using these services because like they're just putting it on the peer-to-peer network, and I'm like finding it quickly because I have put in effort to find out where their nodes are and then relaying it around. It's not necessarily true that they're even aware that they're using this kind of service, but whatever.
So the service is a public good.
Yes, the service is a public good, and it sucks that I'm not getting paid for it. But like, it's only $40 a month. It's not gonna break my bank.
Significant surplus beyond $40 a month.
Yeah, could do better if I had more money. But like, I do want to switch out the Singapore node because DigitalOcean sucks. Their peering sucks because it's Asia. Like, no one has good peering in Asia.
I understand you're using the internet for the traffic. Have you considered using some private lines so that it's solvable?
Yes. So the question was, I'm using the internet for the traffic. Have I considered using some private lines? The answer is, I would love to if I had lots and lots of money, because private lines are not cheap. And for $40 a month, sure, the bandwidth is tiny, but you can't exactly go to someone who has a bunch of undersea cables and say, hey, I want to pay you almost nothing to use almost none of your bandwidth, because like they expect big customers and they're just going to charge you out the nose because it takes them a bunch of time to set it up. I would bet you cannot find a private line for under $40 a month anywhere, even within the US, let alone like across the ocean. Any further questions? Okay, thank you.